See, the first thing everybody talks about, things like quantum supremacy and things like that, right? And actually, that quantum computing is going to make things much faster and all of those sort of things. So I am not very sure if everybody understands it correctly. So do you guys, or do you guys have an idea why are quantum computers fast actually? Or what is it that makes them fast? Okay. So did you guys hear this term quantum supremacy? Did you guys hear this word quantum supremacy before? Anybody? No, nobody heard quantum supremacy before? You should have seen it in some news articles and things like that, right? People said Google achieved quantum supremacy and all of that. Okay. So quantum supremacy basically means that finally there is a computation that was done faster than in the classical world using a quantum computer, right? So that's what quantum supremacy means. So I just want to talk 2 minutes about this to understand what it means before I delve into some of the operators today. So what do you say? We say we have qubits, right? We have multiple qubits. That's what we say, right? Qubit 1, qubit 2, and whatever, qubit n. Right? This is what we say. And then we say that all of them are in a superposition state. Correct? So, for example, if you kind of say something like, the Google computer had 53 bits, 53 qubits. So how many states can they be in? 2 to the power 53, right? In 2 to the power 53 different superposition states simultaneously. Correct? If each state is 0, 1, 0, 1, 0, 1, then 53 states can be in a total of 2 to the power 53 different configurations. Makes sense till now?
Yes, sir.
Correct. Now all of them can be entangled in certain ways. We can entangle them. We can entangle those bits in however we want. Now here is the issue. We are saying that somehow this is going to be faster, right, than a classical computer. See, even in a classical computer, if you have 53 classical bits, they can be in 2 to the power 53 different configurations. Not simultaneously, but they can be in 2 to the power 53 configurations, right? Now, what makes this faster is, if you really think about it, and this is where most popular books on quantum physics or quantum mechanics go wrong. If you actually measure this, let's say you measure this state, then it will randomly collapse to one state, correct? Depending on the amplitudes. Correct. Now each one has, let us say, some amplitude, right? Alpha 1, alpha 2, alpha 3, alpha n, right? Where all these alpha i's are belonging to some complex number set. Correct. So it is some amplitudes that you have. So with what probability it will go? Probability is basically alpha 1 square plus alpha 2 square plus alpha n square root of. Correct? That is the probability with which it will one configuration, you will see one configuration. Now the point is, if you measure this, you will only get a random configuration. You will get a random answer, which is useless. So what you should do finally, why is quantum computing so fast, is because you have these 2 power 53 superpositions simultaneously. You should somehow manipulate these amplitudes such that the wrong amplitudes cancel out and the right amplitudes get kind of increased, so that the probability of the right answer gets higher and higher. So all of quantum computing is just about manipulating these amplitudes. Is it making sense, whatever I'm trying to tell you?
Yes.
Maybe I'll try and give you another example. Maybe this will be easier. See, if you kind of say this, right? If you say you have a bit which is 0, 0, right? And then let us say this bit can remain either as 0, 0 or it can become 0, 1. Let us say there is a half probability of these two happening. Correct? So a bit flipping into 1 or remaining as 0. Probability. So this is your classical world, right? And so if you say this, if it is 0, 0, it will remain as 0, 0. If it is 0, 1, let us say it will become 1, 1. And let us say some probability here is again, this is given 3/4 and this is given 1/4. Then it is very easy, right? If I ask you the question saying from 0, 0 to 0 to 1, 1, what is the probability? It is 1/2 multiplied by 1/4, right? Correct?
Yes. Yes. Yes.
1/2 into 3/4, so whatever. So this is how the probability works, right? Classical probability, absolutely fine. Now in quantum mechanics, what is different? If you see the same scenario in a quantum mechanical state, what will be the fun thing here? The fun thing will be this can be 1/√2, for example, the amplitude. The probability is the square of the amplitude. That's how it is. And this can be I/√2, for example. So what is the probability? So if an amplitude is I/√2, what happens? What is the probability? The probability is actually minus half. Of course, we take the modulus, but the probability is actually minus half, no? Because I²/2. I² is -1. So here the probability actually gets negative, which is not really allowed in the classical world. And this is why you see that in the double slit experiment that you saw, when you opened both slits, right? When you opened both slits, what happened here? You had an interference pattern as if it was in a wave. And if you had closed this one slit, this just became like a particle. Remember double slit experiment? Why did this happen? We said this happens because electrons interfere, or quantum mechanicals interfere with each other in wave-like motion. You can explain that if you understand that the amplitudes can take complex values, which means the amplitudes can cancel out. The square of the amplitudes cancel out, because if something is plus half and minus half, they will both cancel out. That's why you'll have these troughs.
Black pattern.
And if both of them are positive or negative, then you have the peak, right? So this is the key difference, and this is what in superposition state you can manipulate the amplitudes such that the probabilities of the right answer increase and the probabilities of the wrong answers decrease. All of quantum computation and quantum algorithms is just about manipulating those amplitudes to make that happen. That is all that there is. Of course, a simpler said than done, right? How do you manipulate those amplitudes? That's what we will know when we will get into quantum algorithms. But at least is the concept clear? Because I want to make sure that this is clear before I get into explaining quantum algorithms. Right?
Yes. Yeah.
Okay.
Yeah.
Okay, good. This is an important thing. If you already knew, then sorry, I had to spend 10 minutes. But if you did not, then I hope it helped you. Because I was teaching another class, like I said, and they got completely confused. So that's why I was not very sure. So today we will talk about observables and measurements. That's what we'll talk about. And as part of that, we will see some math. We will get into what are called Hermitian and unitary operators. We will see what is Hermitian. I hope you guys already know what is Hermitian, so I don't really need to get into too much detail. If you don't know, I'll briefly explain, but we can kind of see what these Hermitian and unitary operators are, and some properties of this, things like what is a commutator, So this is the basic language of math for actually writing, and we'll also start using the Dirac notation much more formally. I will start using the Dirac notation, and we'll talk about kets and bras and things like that in a little more detail so that we are absolutely clear of what that is. Because from next class, when I start getting into algorithms, these sort of things should not be confusing. Before all of this, let's talk about the 800-pound gorilla in the room. I talked about this many times. I hope all of you know what is a Hilbert space at this point, okay? Anybody wants to take a stab at what is the Hilbert space? Especially somebody who's doing machine learning here. Who's doing machine learning here? Yeah, I get only poor scapegoats, Anik and Madhu. I don't think I'm kind of catching up on you or something, but Anik, for example, do you know what is a Hilbert space? Have you heard this term? Do you know what a Hilbert space is?
No, I don't know.
No, you don't. Madhu, you have an idea? Okay.
Sorry, I was on mute. It's sort of a vector space with an inner product. Sort of.
Yes. I think, yes, you're right. It is. Yes, you're largely right. It is a vector space. Number one, it is a vector space, which is important. So, what is a vector space? Vector space is something that has the norm defined, right? If you have the norm defined, it is a vector space. So the way to think about this, guys, is firstly, when you use the word space, think about it for now as a mathematical construct. Don't get confused by space as a space. Okay. Here we will restrain it to it is a mathematical construct. Okay. Madhu is right. She missed one part of it, but the other two parts she is right. It is a vector space. So what is a vector space? Vector space is basically any mathematical set, a construct that has the norm defined, which means direction and magnitude defined, right? It's a vector. So if you draw something in that space, mathematically it is possible to explain the angle and explain the magnitude of it. It's a vector space. It's a vector space with a speciality, which is the scalar product is defined in that vector space. That scalar product happens to be inner product. We'll quickly look at what that is, right? So what is a scalar product? You have two vectors. If I have two vectors, V1 and V2, for example, I can define what? I can define V1 plus V2. This is defined, right? This is defined even in your Euclidean space is also a Hilbert space, okay? But Hilbert space need not be limited to real spaces only. So here we are going to talk about a complex Hilbert space. But Hilbert space is any vector space with norm and inner product and a scalar product defined. So if you have two vectors, V1 and V2, what is the addition of V1 plus V2? Correct? Simple, Euclidean. Same thing, you have V1 plus V2 defined. Similarly, you have alpha 1 V1 and alpha 2 V2 defined. Right? When you multiply where alpha 1 and alpha 2 belong to real. It is just a scaling, right? It is just scaling. So if you have something like this, and if you have V1, what is alpha V1? Scale the vector, right? This is defined, and I won't get into like this. These are all linear operators. These obey the laws of commutativity, the laws of associativity, distributive laws, all of that. You can go and check it out yourself. Okay, this is very simple. So essentially, it is whatever alpha 1 V1 plus V2 is alpha 1 V1 plus alpha 2 V2. So it is linear, it is associative, it is also commutative, and all of that. Okay, and these are all linear operators. So you can just check that. It's not a big deal. The important thing is now how do you define the scalar product of V1, V2? right? What is the scalar product of V1 and V2? It is defined as the inner product, the dot product, right? Because what is the result of a scalar product? So if you have two vectors, which is whatever, if I have two vectors in Euclidean space, x1, y1, z1, and x1, y1, x2, y2, z2, what is the scalar product? x1, x2 plus y1, y2 plus z1, z2, right? This is just a scalar number. Clear, right? I'm not making anything. I'm sure all of this is very, very simple. Just tell me, guys, it's clear. Otherwise, I have to explain what is a scalar product. Okay. But there should be some response, guys. Say yes, no, maybe, I don't care, whatever.
I'm able to understand, Srini.
You understand from here?
Yes, yes.
Okay, so this is a scalar product. Scalar product is defined this way. This particular scalar product is called the inner product, which is the result of multiplication of two vectors defined like this. The result is a scalar, right? When you multiply this, the result is a scalar. It is not there is no vector answer there.
Right. Yes.
Okay, so that's all. So this is in the Euclidean space. So let us come into the phase space. See, one other thing in quantum mechanics, one other terminology I'll be saying a lot of times phase space. Okay, let me explain what that phase space is so that there is no more confusion. Phase space is nothing but the Hilbert space of all complex numbers. So we'll be using a term. I will keep saying phase space every time. Phase space is just but it is nothing but a Hilbert space of complex numbers. That's it. And so all our quantum mechanical vectors, everything that we deal with in quantum mechanics and quantum computing will live in this space. This is a huge space, set of all complex numbers, complex number vectors. One way to think about it is mathematically bigger than the biggest universe you can dream about. It's a huge space. Everything can, it's a complete space. So all additions, it's a closed space. So everything lies within this space. So if you multiply two complex vectors, they will lie in this space. If you add two complex vectors, they will lie in this space. You do anything to complex vectors, they will lie in this Hilbert space. So it's a huge space. It's more than huge, we should say mathematically it's a closed space. It's closed under the operations of addition and multiplication. Okay. Now, right. Now we have to talk about a few things. And I think we have to talk about operators here and things like that. So I think before that, we will talk about observables now, and we will see what observables are. Within that, we will come into Hermitian operators. So what is an observable? An observable of a state is something that you can observe. Right? It is something that you can observe. So in a classical, so observables can be anything like position, momentum, anything, energy. So the way you write it is function of some state equals x. In the classical world, this is how you will do it. So S is the state, some state. What is a state? Learn to think about the state as a configuration. State is just a configuration. Okay. If you call the state as, let us say, state of this room that I'm standing in, the state can be the position of each table and each chair and bags and TV and myself and the board and everything. So that is the configuration. Now of this configuration, you can measure some observable. That is the function. Whatever you measure, right? You can measure, I don't know, the energy, the temperature of this room, whatever you measure. the value is the value x. X is the scalar value. So this is how you do it in classical mechanics. Or the entire classical world is just this. You have some state, you have some function of that state to measure observable, and then you get some scalar value. This need not always be a scalar value, it can be a vector also. So now we have to, now bringing this into the quantum world, there is some amount of fun that happens when you kind of do this in the quantum world. I will write something and then we will go ahead and kind of explain what this is. Okay, and we will get into the details. And we will talk about each one of these things. This is what we'll break up and hopefully learn in this class. Okay, this is the governing equation. What does this mean? This O means it's a unitary matrix. It's a unitary operator. And like I said, we will see what unitary operators are. First, let us conceptually understand what this means. This psi is some state of the quantum system, some configuration of the quantum system, okay? Some superposition with some amplitudes is what the psi is. What is the lambda I? Lambda I is the, what you call the eigenvalues. And AI are the eigenstate after measurement. So what is it? It's a lot of fancy words and we'll get into each one of those words as we talk about, but first conceptually let's understand. So what is psi here? Psi is a collection of qubits. Think about it like a collection of qubits, okay, with some amplitudes. Each one having some amplitude, collection of qubits. They are interacting, so assume that a lot of them are entangled in some weird ways. It's an n-way entanglement, okay, of n bits. So it's a complex configuration of qubits. Now, what is O? O is some function, but here we are saying that function is limited to being a unitary operator. Now, physically, if you understand what is a unitary operator, physically it says basically the mathematical definition that we'll get to, but physically, if you want to understand what is a unitary operator preserves the norm of the vector. So because here the norm of the vector, the total vector needs to be 1, the square of all amplitudes. Why? Because we are normalizing it, because we are considering the square of amplitude as a probability here. Correct? In our quantum mechanics, the way we have defined the amplitudes are, the square of the amplitude is a probability. That's how I have defined it, right? So for example, if I'm saying 1 by root 2 of 0, I am saying it is 1 by 2 is the probability of that bit collapsing to the number 0. Correct? So 1 by root 2 is the amplitude. So I'm defining probability as the square of amplitude here. And because I'm defining it in such a way, the unitary operator ensures that all the probabilities together after measurement, after applying this operator also equals 1. You understand why that is important, right? So if it collapses to one state, all the other state amplitude should become 0. Otherwise, this definition won't hold, right? Otherwise, that's why there is this constraint on this operator being a unitary operator. Like I said, we will mathematically go through and understand what this is, but physically, but conceptually, if you want to understand what is a unitary operator, it is an operator that preserves the norm of the vector post transformation. Post transformation, the norm of the vector is maintained. Here the norm is 1, sum of all of those square of amplitudes, and the same is maintained. Now, in quantum mechanics, there is, why is it called quantum mechanics? Firstly, because things are quantized, right? That's how the word quantized means, into pieces, into small indivisible pieces. That is what Einstein said in his photoelectric effect, where the energy of light is quantized. It is not really, it cannot take a continuous set of values, right? The set of values are constrained. They have to be multiples of a certain thing. We all talked about it, right? H into lambda, which is C by frequency and other things. So that is why when you measure a quantum system or a quantum superposition or a quantum configuration, it can only fall in one of the few configurations. So when it is under superposition, it can be under any state, but when you measure it, each one has to get into either a 0 or a 1 or a 0 or a 1 or a 0 or a 1. In fact, there's one thing I didn't probably talk about, which maybe we don't need to because we're not really doing quantum mechanics, but you have to understand that there's something called pure states and impure states. 0 and 1 are called the pure states of a quantum system, okay, where it can be either 0 or 1, but nothing in between. Actually, there are some impure states also where under certain circumstances, quantum particles can take values between 0 and 1. But for now and for this entire class, we will only deal with pure states. I don't want to confuse this even more. So let us deal only with pure states. So the eigenvalues and the eigenstates are here only two possible states for each one of those qubits, either 0 or a 1, or a spin up or a spin down, right? Or negative angular momentum or positive angular momentum. There are only binary values. So each one takes a particular eigenstate and the eigenvalue, which is the norm of that state or the value of that state. So you can break it down only like this. It cannot be broken down. For example, if you have something like this, if see what happens typically in classical mechanics, you have one force acting in this direction and you have another force acting in this direction. If two forces are acting in two different directions, the resultant force can be something like this in this direction. Correct? You can actually have that in classical mechanics. In quantum mechanics, you can't have amplitude can be in this direction and this, but when you measure it, the amplitude can only be here or here. It collapses to only those pure orthogonal eigenstates. It does not collapse into something else. You cannot, or at least for now, let us understand that it cannot. Making sense till now?
Yes.
Yes. Yes.
So that is what that is. So unitary operator physically is something which maintains the norm. Now we will see there are a lot of properties of unitary operators and Hermitian operators that we will see, but I think at least conceptually you've gotten it to some extent. Okay. Let's see what we have to get to adjoint operators and no, maybe you don't need. Yeah, maybe let's go to Dirac notation a little bit, okay? Because I think I may not have talked enough about this, right? Now we all know Paul Dirac, and so what I told you, just keep it in mind. We will get back there in 10 minutes, okay? Once I finish a little bit with Dirac notation. Hold on. Come back. So what is Dirac notation? Everybody knows, right? Paul Dirac, great physicist, did this, did that. He actually defined a fantastic notation for dealing with quantum mechanics, and we still use it. That's the most popular notation. So I think we already used something called kets, right? Where we said ket is written like this, which is just nothing but a quantum vector, a quantum configuration, that's all. Okay, of however number of qubits that we want. If it is 2, then we will write 5, comma psi or whatever. Okay, so this notation is called a ket, K-E-T, and we will be using this again and again and again. So you got to get very familiar. When I put straight line and a greater than equal to and I write something in between, that is just a quantum state configuration, a vector. That is all that there is. Now, there is something else that we need to understand before I bring out the bra part of it. Okay, so if you see last time, let R1 and let's go to the classical world and let's see a configuration and then we'll kind of be clear. Let us say we have these vectors that I talked about last time again. And let us say this is R1 and this is R2. So this is a row vector and this is a column vector. R1 dot R2 is well defined, right? We just wrote it. It's X1, sorry. Somebody should correct me then. So you can do the dot product easy. Now if I ask you to add these two vectors, can you add these two vectors? Can you add these two? Can you add a row vector and a column vector?
We can only multiply, not add.
Correct. You cannot add these two. But what did I define initially? I said if in a vector space, if two vectors are in a vector space, vector addition and vector multiplication should be defined on it, right? For it to be called a vector space. I did say that.
Right.
So
Yeah.
now you cannot add these two vectors because simple common sense tells you how do you add. Then what is, as a mathematician, what is our answer? These two belong to different vector spaces. Get what I'm saying here?
Yes.
Because if these two belong to the same vector space, I should be able to add them. But I can't add them because I have defined a vector space such that vector addition has to be defined on it. Now you can't add these two vectors, so I will call them these two vectors to be of different vector spaces. Usually what we do, and this is just convention, okay? Or at least in quantum mechanics, this is a convention. In classical mechanics also we do this, but probably it's not taught as well. If you do Hamiltonian mechanics, it will come more, but we are not probably. See, what we generally say is R2. Okay, the convention, according to convention, the column vector, which is R2, okay, which is the column vector, we say belongs to the vector space V, and R1, which is the row vector, we say it belongs to something called V star, which is called a dual vector space. Again, this is just terminology you got to be aware of, because when you're working in this space, you will see a lot of times dual vector space. Dual vector space, all that it means is it is a vector that you can do a dot product with but cannot add. We'll formalize the definition in a second, but that is a dual vector space. Okay. Another way to write it is, what do we say? We say scalar product of R1, comma R2 is some real number, R belonging to R. Correct. Another way to write this is, the way we kind of write this is R1 and we just put a dot equals R2 vector, which is to say that if you multiply R1 with R2, you will get the dot product or the scalar product answer. It is just a way of writing, a notation. You understand this much, right? Till now? It is just a notation. Because these two don't belong to the same vector spaces, they're different vector spaces, but it doesn't matter. All that you're saying is the scalar product of a vector with another vector gives you some scalar answer, which is a real number. Here, all that you're saying is a scalar product between R1 dot equals R2 vector means if you multiply this R1 with R2, an inner product of R1 and R2 will give you some scalar answer. That's all that you're trying to say. Okay. This should be familiar. I don't know. This should be familiar in the sense if you have done classical physics, this will come. Okay, especially Hamiltonian physics, this will come. Now we see in quantum mechanics, all that we do is we take a definition from real world and modify it to suit our thing. So the same thing we will do here. And this is important because this is how the definition of a bra comes from. Okay. So I saw this is a ket. So the way I do it is a scalar product of a psi comma a phi, let us say, equals C, which belongs to C. Then the way I write it is SP of psi dot equals phi. No, not equals phi, sorry. This quantity is known as the bra of phi. This is a ket and that's a bra. So that is how a bra is defined. A bra is defined as that quantity that when multiplied with the ket will give you the scalar product answer. Get what I'm saying here? If this is phi, then you can write phi here also because it's still the phi, it's not psi, but that's okay. But it is basically saying that which is multiplied by this will give you the scalar product. That is defined as the bra and this is defined as the ket. So the vector is defined as the ket and the vector in the dual vector space that when you multiply with this will give you the scalar product is defined as the bra. So if you want to write a scalar product, you write it like this, psi comma phi, which is,
Okay.
this is basically your bra and this is basically your bra and your ket together is bracket. Understand that simply. Guys, do you get this, right? This is simple definitions only, nothing great, but you need to understand this terminology. So if you really want to understand this, what did I tell you? Just understand it like this. If you want to do this, if you want to understand, saying that this is a state space and this is the dual space. And if you try and understand this, right? This is your ket. In dual space, it becomes your bra. This is what it is. And scalar product is defined as that is all. So this is, and if you combine them, this gives you the scalar product. So if you multiply this with this, it gives you a scalar product. So when you write a scalar product, you just write psi, phi or psi or whatever. Okay. If you multiply this psi with psi, the answer has to be 1. The scalar product of something with itself has to be 1. It has to be norm 1. Right? That's commonsensical. Because dot product also intuitively gives you what? The similarity between two vectors. So if you do the inner product, dot product of psi with psi, the answer will be 1. The psi with phi will be how much ever similar psi and phi are within their eigenstates. Okay, so that is what that is going to be. I hope at least this is a little bit clear. Like I said, now we'll have to get into some math because otherwise we cannot write those algorithms anymore. I'm trying to make it very, very slow, but now we will have to get into operators and we will have to see what are, yeah, maybe first we will see what is an operator and then we will actually see whatever it is. So what is an operator? And we said operator will be a unitary operator, but first let's not get into the definition of unitary. Let's first see what an operator is. Right, and some of these things you may have to prove, but so an operator is very simple. So operator is something that operates, right? So you take an operator A hat and then you make it on some ket psi. The answer will be some state psi hash or psi dash or something, right? Some change you will do. In this A is called an operator, which is the same as a state function that we talked in the classical world. Okay, it could be an energy, it could be whatever you're measuring something, you will get another configuration. Now that configuration we saw will be in eigenstates and eigenvalues, but we will see that a little later. Now I will not get into this whole definition, but this is linear. And in addition, it is associative and commutative. If you want, you can kind of work on it and prove it yourself. This is not very difficult to prove. So all that you have to say is, you know, if you apply this to some A1 psi 1 plus A2 psi 2 state, then you can take it out and you can prove that it's basically associative. Correct. Similarly, it is commutative. A plus B will be equals to B plus A. So if you have this plus and another one operator B, then that becomes B plus A. A plus B equals B plus A. In addition, it is both associative and commutative. The real fun starts when you are trying to do multiplication. Multiplication of operators in quantum mechanics is not commutative, which is this is a very, very important law. In classical physics, this is commutative. In the sense, if you measure the position and then the momentum, that answer is equal to if you measure the momentum and then measure the position. Correct? This is not true. First, let's even define that, right? So if you have A star, B star of some state called psi, this can be taken as A of so first you apply the operator B and then you apply the operator A. That is how it is defined. And this is not commutative. Naturally, this is not commutative. It is not natural. You can only see this as part of our initial set of experiments. If you think about like that color and hardness, you will see why this is not commutative. Correct? If you measure the color first and the hardness later, or the hardness first and the color later, it is different, right?
Yes, yes.
So this is not commutative, and this is very, very important. And we define an operator called the commutator, which is a quantum mechanics operator, which is written as this is equal to the difference. when you apply A and then B minus when you apply B and then A. And this will be not equal to 0 largely for a lot of operators. It's not universally true. For some operators it is, but at least at the level that we are going to be doing this, for all operators this will be non-zero. And this you can easily see is one more way to understand the uncertainty principle. Right, where you can't measure the position and momentum at the same time. Why? Because multiplication of operators in quantum mechanics is not commutative. That is the reason. Proof of this is too involved right now. We'll not get into the proof. We'll have to use Schrodinger's equation and prove it. That is too much math. It is not necessary. It will probably take 3 or 4 classes just to prove that one thing out. So this commutator is very, very important. Yeah, let's try and now let's talk about what is a Hermitian operator and what is a unitary operator. At least the mathematical properties. Hermitian operators, maybe when you're doing deep learning, you might have come across Hermitian operators, but an operator A is called Hermitian if and only if do you know what the symbol is? Did we talk about this? Conjugate transpose. Did we talk about this plus symbol at all?
Yes, we did.
Yes, this is the complex conjugate. When an operator is equal to its complex conjugate, it is known as an Hermitian operator.
Yes. Yeah.
This is the definition of what is an Hermitian operator. Now, one specific condition of Hermitian operator is that if you actually have read about Hermitian operators in linear algebra, the eigenvalues will always be real. The eigenvalues of a Hermitian operator will always be real. I think some of these things you may have to, at the end, I'll probably give you a few exercises. You can try them on your own by using some postulates and things like that that we talked about. But so you can also think about this as the adjoint operator, right? Because the bra and the ket thing, the scalar product, it's basically the adjoint operator also. You can also think about this as the adjoint. The adjoint is the same. See in your real world, you only had transpose. Right? You had an operator, you had a matrix, and you had a transpose of it. Only in complex number world, you will have conjugates. Correct, right? If you have something like 2 plus I, 1 minus I, 4 plus 3I, if you have this, then what is the transpose of this matrix? What is the transpose? 2 plus I, 1 minus I, and then you change this, right? Is this right?
Yeah.
Now, what is the conjugate of this?
2 minus I. Yeah. 1 plus I.
So this is the adjoint on the complex conjugate of this. So here what I'm saying is, if an operator is such that the operator is equal to its own adjoint, is equal to its own complex conjugate, then that particular operator is called an Hermitian operator. And we'll talk about this operator again and again a lot. A lot of operators in complex numbers will become Hermitian. When we are talking about some of the gates like Hadamard gate and all, you can actually test now, because remember in introductory session I told you what a Hadamard gate is. And Hadamard gate is an Hermitian operator. You can test it out. You can just multiply it with something and see that the result will be same. And that is why it has the property of doing it both from classical to quantum superposition and superposition to non-superposition state. It can do both. This is the Hermitian operator. Your Hadamard gate is a classic example of a Hermitian operator. Though at that point I did not use the word Hermitian because we were not there with linear algebra yet. I don't want to get into more details. If you want, I will see, my request is between this class and next class, do a little bit of reading on Hermitian operators and Hermitian matrices. It's very common in deep learning. So if you are doing ResNet type architectures and things like that, you will actually see that your whatever skip connections you have will end up behaving like Hermitian matrices. Okay, so and the eigenvalues will always be real. Even for a complex operator, the eigenvalues will end up being real always. And again, there are proofs for this. You can prove that any standard complex analysis textbook will have all of these proofs. Okay, so we don't have to. If you want some books, I will refer, but they're all standard proofs. Okay, standard, I don't know, standard graduate level math, I think. So complex analysis will always you'll have real values there. Okay, the eigenvalues. See, again, eigenvalues and eigenstates and eigenvectors you have to be very, very familiar with. Okay, linear algebra, 101 of linear algebra, you should be familiar with. Eigen is a German word. Can anybody tell me what eigen means? No. Okay. Eigen means purpose. It also at some level means standard. Though I don't know why it is called eigen, but I think because they are the standard, at some level, standard interpretations of that matrix, I guess, or the ones that don't change, right? Those are the eigenvalues. Eigenstates or eigendirections are those directions which are key to that operator, right? In what directions does it not change under a transformation? Don't tell me you're having confusions on things like this, right? If you have a vector like this and if you rotate it, anything that is lying on this is not changing, no? So that is the eigen direction of this transformation of this vector as you're rotating it through. Rotating it through, when you're rotating a vector, what are you doing? You're multiplying it by a matrix. You multiply with some matrix, you rotate it. See, all operations are nothing but rotations. That's all that they are. Any operator that we are using finally is nothing but some rotation in that Hilbert space that I talked about. That's all that I'm doing. See, right now we assume a finite dimensional Hilbert space. Normally you assume an infinite dimensional Hilbert space, but for simplicity's sake, right now let us assume a finite dimensional Hilbert space as you're doing these transformations. Ideally, Hilbert spaces are infinite. Hilbert spaces are not finite. But without any loss of generality, you can call it finite and still prove all of your results. You will not have an issue proving your results whether it's finite or infinite. Okay. Now let's talk about unitary operator a little bit. What is a unitary operator? Unitary operator is again very simple. An operator where the inverse of it is equal to its adjoint, that is known as the unitary. This operator here is a unitary operator. It's a stronger condition than Hermitian, but here the eigenvalues are complex numbers. They are not real numbers. They don't need to be real numbers. Though in a lot of specific cases, they will end up being real values. In fact, they will end up being 1 in a lot of specific gates that we will talk about. And see, why am I spending so much time with an operator? Please remember, what you are going to be talking about as quantum gates are nothing but operators. A quantum circuit is a collection of quantum gates. Each quantum gate is nothing but an operator. You are doing something with it. A C0 gate or whatever, or a Hadamard gate or a Toffoli gate or whatever we talk about, those gates are all going to be operators. So it's important to understand these things, because then only you can create a quantum circuit, which is nothing but a collection of operators. So you're going to put operators in line, which will tend to create a circuit, which will finally give you some result. Right? So that is what it is going to be. So an operator is not just a fancy word. It is finally what is a gate. So as you're designing quantum circuits, because that's what we really need to do at the end of the day, design quantum algorithms and design quantum circuits, you will be using these notations, these operators. It's a unitary operator. So what results from this also is equal to identity, right? Because if this is equal to inverse, then the operator into its adjoint is also the inverse, the identity. Correct? Simple. This implies this. So this is the governing equation. For a unitary operator, the operator and its adjoint together will give you the identity. This is the defining, this is the definition of what is a unitary operator. And the physical understanding of a unitary operator is it keeps the norm. And you can test it out. You can take actually Hadamard gate is also unitary. You can take the Hadamard gate and write this equation. One other thing is, if A and B are unitary, then is also unitary. This also falls into another very important property I talked about in the initial days, where I said every quantum gate is reversible. That is, if you apply a quantum gate once, if you apply the same gate again, you should get back the same result. You should actually be able to prove that with this. If that needs to be true, that can only be true if the operator is unitary. That's probably a good way to think about it. Right? What you're saying is A of psi equals psi. This statement is only true if A is unitary. This is a good way for you to understand what I'm talking about, is try and prove this. Say if this is not unitary, then what happens? You understand what I'm saying here, right? If you apply the same operator twice, you should get back the original state. You remember, guys, what I talked about in the introductory session?
Yes.
Yeah, Shri.
So that this implies this can only be true if A is unitary. Okay? See, the physical understanding is the fact that the norm has to be maintained after the transformation. Okay? But this is the mathematical necessity. Somebody asked me, why do we use complex numbers for quantum mechanics? I hope I made the reason very clear, because if you don't use quantum numbers for amplitude, complex numbers for amplitude, you cannot explain interference. Interference cannot be explained. That is why you use complex numbers. Actually, one simple way to understand complex numbers, Ramya was asking me, is everybody when you were a child told you that -3 into -2 equals +6. Did you ever think why? Why should two minuses result in a positive number? When you multiply two positive numbers, they are positive. When you multiply a positive and negative number, it turns out to be negative. When you multiply two negative numbers, the result turns out to be positive. Isn't it a little bit arbitrary? Yeah, so maybe you guys are not as weird as me to think about those sort of questions, but you can only explain that if you imagine real numbers to be a subset of complex numbers. Otherwise, you cannot derive that. Unfortunately, they don't teach you the derivation in school. The teacher just tells you, listen to me because I'm telling you. That is the first thing in math. Never listen to anybody because they're telling you. Prove these things. They're all standard proofs. The reason I'm not going through that in class is because I don't think this is the best use of 1 hour that I've got with you to go through each, because each one of those proofs will take 3 hours. Okay. But you should at least, not if all, you should at least try and solve some. At least that lets you start writing this Dirac notation first. Okay, bras and kets. Because if you can't write those kets and bras, then there's no point here, because the whole world is just bras and kets, and that's what you do. Okay. And you're also understanding why it is eigenvalues and eigenstates, right? It is eigenvalues and eigenstates. The physical meaning is because the quantum world is quantized. In the sense, energy or position or momentum or anything cannot take any value that it wants. It can only take certain values. Those certain values and its multiples. That is essentially what are your eigenstates of the measurement. Because ideally, from a superposition, think about it. Your particles are in superposition. You want to measure it. Why, if there are 53 qubits, why are there only 2 to the power 53? Ideally, each spin can be an infinite number of spins. Why is spin only up or down? Spin can be up 2 degrees. It can be anything, no? But it is not. That means it is quantized. Only 2 states possible. That is how nature works. Because in classical world, you can't do that. In classical world, if you apply forces at different angles, you will get whatever you want. You can measure this at any level. But in quantum world, you can't. That is why it is eigenstates. That's why when you measure it, it becomes something called lambda into whatever psi or whatever you want it. This is the eigen value and this is the eigenstate. It falls into a combination of eigenvalues and eigenstates. It cannot just fall into any state. That is why Hermitian matrices are very, very important, because you can find the eigenvalues and they're all going to be real. So it makes a lot of computations very, very easy for you to do it. And also because your eigenstates are normalized. Even after measurement, they should be normalized. What do I mean they should be normalized? The probability should equal to 1, which is this should always equal 1. The scalar product of psi with psi should always equal 1, both before measurement and after measurement. This is normalized. Otherwise, you have a problem in quantum mechanics. Actually, there are conditions where this does not hold true, and there's a whole load of literature around that. That's probably the entire part of string theory, but we are not getting into physics. So, in fact, the best way to understand quantum mechanics is take physics out of it. Just start understanding amplitudes. The square of amplitudes are probabilities. There is some amplitude. That amplitude is some property of a state of a configuration. That's it. For a configuration consisting n particles, each particle has some amplitude. That's all. What that amplitude means, we don't know. but we do know that the square of that amplitude gives you the probability of that particular state, particular configuration. Okay, and negative probability doesn't make any sense, but in quantum mechanics it makes sense because there is interference. Normally it doesn't mean anything to say there is minus 30% chance of rain. It means jack shit, but in the quantum world it means something because you have probabilities as I can be an amplitude, so I square is a probability. Because you can explain interference, otherwise you cannot explain interference. Okay, fair enough. And all the eigenstates will be orthogonal right now because we are talking only pure states. Again, when you talk about impure states, the eigenstates need not be orthogonal, but right now, like I'm saying, limiting it to orthogonality. Limiting it to orthogonality. Next class, I am going to actually try and get into a real example of trying to do a regression problem. Okay, using quantum mechanics, using superposition. How do you do regression using superposition? That's what we'll try and talk about. Okay, and then maybe we'll talk about Grover's algorithm and whatever, and then we will try building our own algorithms. That's my goal. And from now on, I start focusing on machine learning algorithms because I guess that's where that's what I know. For example, I don't know too much about non-machine learning. We can also do sorting and searching and things like that. But I will start getting into trying to understand how we can do machine learning algorithms. At least we will make a beginning. I think now you have all the fundamentals. Enough about the fundamentals of quantum mechanics. I think you know some basic notations, some basic types of matrices, basic types of operators. You kind of know those things. So now we can get into trying to see how does, for example, how do you do a least square regression, for example. We all know how to do a least square regression in classical world. How do you write a least square regression method using quantum theory, using quantum mechanics? Okay. And then by this time, I would also expect you to please install Qiskit on your laptops. Use the Anaconda distribution. It's the easiest. Just use Anaconda and install it. It's Python, simple. It's just pip install Qiskit. It'll install it. Maybe if you have a few, have all of you installed it, right? Or anybody not installed yet?
I didn't.
Yeah, so just install it, Ramya. It's very easy. If you have any trouble, just call me. Okay.
Okay.
It's very simple. Just download the Anaconda distribution. I know you're not familiar with Python and all. Don't worry. Sometimes throwing you at the deep end is the best way. Because
yeah, for the first time I installed Atom.
Atom, huh? Okay,
Yes.
That's fine. No,
So I'm still there.
Yeah, what I'm essentially saying is there is no easy way, right? I have tried making it as simple as possible, but now it's time to get into the math and get into those algorithms. And guys, if there is anything about it that is extremely confusing still, then I think the rest of those things I will also try explaining as we get along. Because there are still a lot of results, global phase and all of that, but I don't think we need to spend all of that time here. In the algorithm, when we will come to that place, I will explain it. Okay, that's how we will do it.